Hi everyone! Today we're going to be talking about the difference between relations and functions. Our objectives for today are that students will be able to analyze relations and functions, identify the domain and range of functions, and determine if a relation is a function. Let's get started. What is a relation? A relation is a set of ordered pairs. A relation can be shown in a table. It can be shown in what we call a mapping. It can be shown in a graph, or it could be expressed as an equation. The set of x values in a relation is called the domain, and the set of y values is called the range. So it's important to remember, domain is the x values, range is the y values. And last but not least, a relation with distinct points is called a discrete relation. All right, so we call it discrete if it has distinct points. A relation with connected lines or curves is called continuous. Now, a function is a relation in which each element of the domain is paired with exactly one element of the range. So in simple terms, what this means is that the x values cannot repeat in order for it to be a function. All right, so the x values do not repeat in functions. So if the x values don't repeat, the relation is a function. So for example, if we're given these set of points, so we use the brace, and then we're given 0, 1, we're given -5, 2, we're given -6, -2, and we'll do one more point, and we're given 5, 7. All right, so there's our set of ordered pairs, or our relation. This is in fact a function because none of the x values repeat. So we look at the x value, 0, -5, -6, and +5. None of these repeat. We don't ever use the same x value twice. So it is a function. Now if you were given these set of points, oh, that was a terrible brace. Let's see. There we go. We've got our brace, and we've got -7, 2. We're given 6, -1. We're given 6, 2. And -3, 9. All right, this is not a function because we use 6 twice as an x value. 6 repeats. The x value repeats. So this is not a function. All right, and I just realized that it was written right here in your notes too, so this means x values do not repeat. Highlight this, star this. This is an important piece of information. All right, x values do not repeat in functions. All right, and I had to throw this meme in here because I just love it so much. All right, Yoda telling you, function it is not if an input has more than one unique output. All right, so that's Yoda reminding you that x values can't repeat. All right, the vertical line test. So we use the vertical line test to determine if a relation is a function. So in order for it to be a function, a vertical line cannot pass through more than one point in the relation. So if we're given the graph of a relation, we can use the vertical line test to determine if it's a function. So, for example, if we're given this linear function where we've got a straight line, all right, the vertical line test tells us that if we were to take a straight line and run it across the relation, the graph, all right, so think of it as you're taking a ruler and you're sliding a ruler across. So for example, here's our ruler. If we take the ruler and slide it across the graph, it's only touching our line at one point. It cannot touch our line at more than one point. So right here, it's touching our graph at this point right here, just one point. Now if we slide our ruler a little bit further, all right, see, I don't know why the dot went with it. The dot shouldn't have gone with it. Let's move that dot back. I think because I drew the dot on the ruler. All right, so over here, right, it's touching it at just this single point. Now if we slide the ruler across, oh well, now it's touching it at a single point here. A single point. It's only ever touching it at a single point. Now for the not a function, how we use the vertical line test to determine if it's not a function, is say we have the graph of a circle, all right? There is an equation of a circle, right? You should have learned last year in geometry. So we have the graph of a circle. Now if we take our ruler and, oops, I want my ruler. If we take our ruler and run it across the graph of a circle, it's touching it at that one point right there, but it's also touching it at a second point. So because our ruler or our vertical line is touching the graph at more than one point, it is not a function. All right, so our directions for these examples, we want to find the domain and range of each function, then determine if the relation is a function. What I want you to do is cross off this last line of the instructions where if it is a function, state whether it's one-to-one. I don't want you guys to worry about that, all right? So you can cross that out. We're just going to determine the domain, range, and is it a function. So first, domain. Domain, we want to look at all the x values. So we've got -1, 0, 4, and 6. So our domain is all of our x values, and we want to write them in order from least to greatest. So -1, 0, 4, and 6, and it works out that they're already in order for us. Now our range. Range is all of our y values. So -9, -5, 3, and -2. Now we want to write them in order from least to greatest. So -9 comes first, then -5, then -2, and then 3. Now, is the relation a function? Do any of the x values repeat? The answer is no. None of the x values repeat, so yes, it is a function. Number 3. Number 3, our relation is given to us in a table. So our domain is going to be all of our x values in the table, and we want to list them from least to greatest. So our domain is -4, 0, 2, and 7. Now our range is all of our y values in our table. So the range of our function is going to be -8, -1, and 3 is used twice, so we only have to write it once. All right, you don't have to write 3, 3. You just write the 3 once. Now, is the relation a function? So we ask ourselves, do any of the x values repeat? The answer is no. None of the x values repeat. All right. If we're looking at the y values, we notice one of the y values repeats, but that's okay. What determines if it's a function is if any of the x values repeat. So we would say that yes, this is a function because none of the x values repeat. All right, number 5. Number 5 is a relation given to us in a map. All right, we're mapping our relation here. So in order to write points, what we want to do is look at the map. So we're saying for this x value, we use this y value. So our point would be -4, 0. Then we're saying for -2, the y value is 3. So our second point would be -2, 3. Now, our last x value is 5, and every time we have an x value of 5, it's going to use the y value of 7 and 9. So this gives us 2 more points. We've got 5, 7, and 5, 9. This is how we can translate mappings to points. All right, so now we can look for our domain. We want to look at all the x values. We've got -4, -2, 5, and 5. So domain, -4, -2, and we only write the 5 once. We don't have to write it twice. Range, 0, 3, 7, and 9. 0, 3, 7, and 9. All right, now if you understand the mapping and you don't need to write out the points, that's fine, but I just wanted to show you what the mapping means. What we see when we see the mappings, what we're really seeing is 4 points. All right, and now to determine if it's a function, we ask ourselves, do any of the x values repeat? And the answer is yes. All right, the 5 repeats. We use 5 as an x value for 2 of our points. So no, this is not a function because the x value repeats. The x value of 5 repeats. All right, number 7. So number 7, we're given a graph and we're given multiple points. So it's not a line or any sort of quadratic function or anything like that. It's just a bunch of points. So the easiest thing to do would be to list them out. So start with each point. This point right here, if we're listing out that point, we're going to get -3, 1. Then this point, we've got -3, -2. This point right here, 0, 4. This point right here, we've got 2, -1. And then last but not least, we've got 4, what is that, -5. All right, so there's our 5 points. We've got 5 different points here. Now we want to list out our domain. So our domain is all of our x values. We've got -3, -3, 0, 2, and 4. So our domain is going to be -3, and we only have to write it once, 0, 2, and 4. Our range, all of our y values, 1, -2, 4, -1, and -5. So start with the smallest, which would be -5, then -2, then -1, 1, and 4. All right. Now we want to determine, is this relation a function? Do any of our x values repeat? And the answer to that is yes. -3 repeats. All right, we're using -3 twice as an x value. Another thing you could do is use the vertical line test. All right, so if we've got our ruler, we see that our ruler would cross at and would be touching 2 points right here. So it fails the vertical line test as well because it's touching our relation at more than 1 point. So the answer is no, this is not a function. All right, so number 8, we're doing an odd one because I wanted to do this one with you because it's a little unique. All right, so number 8, we've got a line. It goes on forever in both directions. All right, so the domain of a line that goes on forever in both directions, that means it touches every single x value. So it touches every value on the x-axis it's going to belong to. So we say for a line that goes on forever in both directions, it's going to go in both directions, left and right, and it's going to go in both directions, up and down. So domain is talking about the x-axis, so it's going to be touching every x value. So we say that the domain is all real numbers. And when we write it in interval notation, we say from -infinity to +infinity. All right? If you wanted to use the all real numbers symbol, I would accept that as well. Now the range, all right, we said that it goes up and down forever in both directions, right? This side's going to go down forever, and this side's going to go up forever. So the range of this function is also all real numbers, all right? And once again, I would accept the all real numbers symbol as well. Now, is it a function? So this is a case where we want to use the vertical line test. So we take our ruler, all right, or our straight edge, our pencil, it could be anything. And we see that it's only touching the graph or the line at 1 point, all right? Here it's touching it at single point, all right? If we move our ruler over here, it's touching it at a single point, all right? That means that it passes the vertical line test. So yes, it passes the vertical line test, so yes, it is a function. All right, number 9. Number 9 is a little unique as well, a little different. That's why we're going to do it together. All right, so don't fret, don't worry. Number 9, when we're talking about the domain, all right, we're looking at this graph right here. All right, now, when we're looking at the domain, we want the x values. So we want to know what part of the x-axis is part of our function or our relation. So what we want to do is look at, we want to use, in a sense, we want to use like a vertical line. Okay, so we want to say that our graph, if we were to draw a dotted line, would start here, and the domain would be all the values to the right of it, right? Our graph goes to the right of that line. So that is our domain. We're saying to the right of that dotted line that I just drew. So what we're saying is every x value in this direction is going to be a part of our relation. So for the domain, we would say that it starts at -4, and it's including -4, so we use a bracket, to infinity, and that is our domain. Now oops, I don't know what it just did. Let me rewrite that. Alright, so from -4 to infinity. Alright, now I'm trying to get my eraser, so I want you to be able to see. Now we're going to draw the range in. Alright, so the range of this graph, if we're looking, we know that this direction goes up forever, and this direction is going down forever. So actually, we don't even need to draw the range. We can just see that it's going forever in both directions. So the range of this graph would be from -infinity to +infinity. Now, if we're trying to determine if it's a function, we want to use the vertical line test. So let me get a ruler. Alright, got a ruler. Now, if we've got our ruler or our straight edge, we place it at any and every point on the graph. So if we place it right here, it's only touching at one point. If we place it here, it's only touching at one point. But if we place it here, it's touching our graph at more than one point. It's touching the graph right there, and it's touching the graph right there. So this relation fails the vertical line test. So no, it is not a function. Alright, so number 11, I know it's in your notes and it's an odd, but I want you guys to skip quadratics for now. So we call this a quadratic function because anytime we see an x squared, alright, that gives us a hint that this is a quadratic. We want to skip quadratics for now, alright? We will talk about this later on in the year, or later on in this semester, but for now we're going to skip quadratics because I don't have you guys using graphing calculators. If we were using graphing calculators, we can do this, but for now I'm not going to require you to go out and buy an expensive graphing calculator. We're just going to skip them for now, and when we get to the quadratics chapter, I'll explain how to do this. Alright, number 13. So number 13, we have the equation y equals -7. So if you remember, relations can be presented to us as equations as well. Alright, so we've got y equals 7. Important thing we need to remember is that, I've got this little acronym for you. Alright, we've got HOI and VUX. Alright, each letter stands for something. So anytime you've got y equals a number, this is going to be a horizontal line and have a slope of 0. Alright, so this will help you remember anytime you have y equals a number, it's going to be a horizontal line and have a slope of 0. Anytime you have x equals a number, it's going to be a vertical line and it's going to have an undefined slope. So x equals a number is a vertical line, undefined slope. Alright, so HOI and VUX. That will help you remember. Alright, little acronym. So that's my little trick to you guys to help you memorize that because it's something you need to memorize. So we've got y equals -7. It's going to be a horizontal line. So if we've got an xy axis, and we label it x and y. Alright, now y equals -7 means we look at the y-axis. We go down 7. So 3, 4, 5, 6, 7. Alright, so it's going to be right there. That's -7. And we're going to have a horizontal line at y equals -7. That's what our graph would look like. Alright, hopefully you're using graph paper and it looks much nicer than what I just drew. This is just a rough sketch. Alright, but a horizontal line at y equals -7. Our domain, we look at our x-axis for our domain, it's going to go to the left forever and to the right forever on our x-axis. So that means our domain is all real numbers from negative infinity to positive infinity. Now our range, if we're looking at our y-axis, it's only going to hit the y-axis at -7. This is y equals -7. This is y equals -7. At this point right here, y is -7. So at every point on our graph, y is going to be 7. So if we're writing that in interval notation, we would use a bracket, a 7, and a bracket, all right? So that stands for the range being 7, and only 7. Now, to determine is it a function, we want to use the vertical line test. So let me get a ruler. Now we're looking at our ruler, and we're running it across the green line, across our relation, and we're determining is it a function. So at here, it's touching the graph at a single point, right there. If we run our ruler across, it's touching it at a single point, single point, single point. There's going to be no point on our function or on our relation where it's touching more than one point. So yes, our relation is a function. Alright, at the beginning of the video notes we talked about continuous and discrete relations, and I just want to elaborate a little bit further on those. So first of all, a continuous relation, our definition is that a continuous relation, a continuous relation is a set of data points is said to be continuous if the values belonging to the set can take on any value within a finite or infinite interval. So some examples of continuous relations would be the height of a horse, because this could be any value within the range of horse heights. The time to complete a task, which could be measured to fractions of seconds. The outdoor temperature at noon can be any value within the possible temperature ranges of planet Earth. Or the speed of a car on Route 3, assuming that there's legal speed limits. One thing I want you to note is that continuous data usually requires a measuring device. So it requires us to measure something, whether that be with a ruler, a stopwatch, a thermometer, a speedometer. It's something that's measurable. Now, a function, if in the graph of a continuous function, the points are connected with a continuous line. And since every point has meaning to the original problem. So it's important to know that with a continuous function, all the points are connected and it's a continuous line. So for example, our graph, the graph of a continuous function, you can draw it without lifting your pencil from the paper. So this right here is an example of a quadratic function that is continuous because you can draw it without lifting your pencil from the paper. The domain of continuous functions, when we have a set of input values, it's consisting of all the numbers in an interval. And basically in plain English, this just means a continuous function allows the x values to be any points in the interval, including fractions, decimals, and irrational values. Alright, now let's elaborate a little bit more about discrete relations. So a set of data is said to be discrete if the values belonging to the set are distinct and separate, so they're unconnected values. So for example, a few examples of discrete relations would be the number of people in your class. There can't be fractional parts of a person. So discrete, it has to be distinct. Okay, the number of TV sets in your home. You can't have parts of a TV set. You either have one TV set, two TV sets, no TV sets, all right? Otherwise, it doesn't work. If you have a part of a TV, like just the screen part without all the computer parts that go with it, it's not going to work. It's not a TV. The number of puppies in a litter. You can't have part of a puppy. The number of questions on a math test, all right? There's no half questions. There's either a question or no question. So basically what I want you to recognize is discrete data has to be counted. It has to be whole numbers. It has to be, the description of the task usually is preceded by the words the number of. So those are keywords that you will see to tell you that it is a discrete relation. So we know that discrete data is counted. We know that we're going to see the words number of. And if it's a discrete function, All right, in the graph of a discrete function, only separate, distinct points are plotted, and only these points have meaning to the original problem. So a discrete graph would look something like this, where we just have dots all over the graph. All right, it's a series of unconnected points. So for example, scatter plots would be discrete functions. The domain is a set of input values consisting of only certain numbers in the interval. So it's just the certain numbers, just the certain unconnected points, just those certain points that you've plotted. That is the domain. So basically, in plain English, a discrete function allows the x values to be only certain values in the interval, usually only integers or whole numbers. All right, so why do we care? Why do we care about the difference between a continuous relation and a discrete relation? Well, when we're graphing a function, especially one related to a real-world situation, it's important to choose an appropriate domain or x value for the graph. So for example, if a function represents the number of people left on an island at the end of each week in Survivor, like the TV show, an appropriate domain would be positive integers. We can't have negative people, and we can't have half of a person, all right? So half of a person is not an appropriate answer for any of the weeks, and you can't have negative people. All right, so the graph of the people remaining on the island would be a discrete graph, not a continuous graph, because it can't be negative and it can't be partial. So basically, discrete and continuous really matter when we're dealing with real-world situations. All right, the last thing we're going to talk about today is even and odd functions. You can cross off the words and one-to-one functions. We're not going to talk about those just yet. All right, so we can classify the graphs of functions as either even, odd, or neither. So first of all, what makes a function even? So a function is an even function if f of negative x equals f of x. All right, so just write that down for now. Probably doesn't make much sense. I will explain it, don't worry. All right, so a function is an even function if f of negative x is equal to f of x for all x values in the domain of f. So the right side, what this means is the right side of the equation of an even function does not change if x is replaced with negative x. So even if we make our x value negative, it's still going to be the same y value, okay? And even functions are symmetric with respect to the y-axis. This means that we could fold the graph on the y-axis and it would line up perfectly on both sides. So it's symmetric with respect to the y-axis. Now, what makes a function an odd function? Well, a function is odd if f of negative x equals negative f of x. So what this means is every term on the right side of the equation changes signs, okay, if x is replaced with negative x. So odd functions are symmetric with respect to the origin, all right? Or you could think of it as with respect to the x-axis. This means that we can flip the image upside down and it will appear exactly the same. So what this means here is if we replace every x value with that same x value but negative, our y value is still going to be the same. If we replace every x value and make every x value negative here, the y value also becomes negative when we're dealing with odd functions. So it's important to know this, even, reflect across the y-axis. Odd, the y becomes negative and is reflected across the origin or the x-axis. All right, if we cannot classify a function as even or odd, then we just say neither. All right, so now we want to determine graphically, using possible symmetry, whether or not the following functions are even, odd, or neither. All right, so what we want to do first is let's look at number one. Okay, so number one, first thing we want to ask ourselves is if we were to draw a line down the y-axis, is it symmetric? Can we fold it across the y-axis and it be the same? All right, the answer is no for this one, so it is not even. Now, if we were to fold it across the x-axis or reflect it across the origin, would it be exactly the same? Is it symmetric? The answer is No. So it is not symmetric with respect to the y-axis or the x-axis. So we would say that this is neither. All right, so this is neither even nor odd. Now, if we're moving on to number 2, first thing we want to ask ourselves is if we draw a line down the y-axis, is it symmetric? Answer is yes, it's symmetric. If we fold it in half, it'll fall on top of each other, okay? So it is symmetric to the y-axis. So then we can say that number 2 is even. Number 3, is it symmetric in respect to the y-axis? The answer is yes. So right off the bat, we know that number 3 is even as well. All right, number 4. If we draw a line down the y-axis, if we were to fold it over, would it be symmetric? Would it go right on top of each other? For number 4, the answer is no, because if we were to put this side, fold it over to the other side, it would go right here, not up here. All right, so it is not symmetric to the y-axis. Now, how about to the x-axis? All right, so if we were to fold it over, would it be symmetric? And one way to be sure of this is if we were to turn the paper upside down. So what I want everybody to do right now is flip your paper upside down, and does it look the same? All right, so let me see if I can do it on here. Nope, I can't do it on here. All right, but I want all of you to turn your paper upside down, and you'll see that it still looks like this. So that tells us that yes, it is symmetric to the x-axis, or symmetric with respect to the origin. So this would be an odd function. Number 5. It is not symmetric to the y-axis. It is symmetric to the x-axis, because if we were to turn our papers over, it would be the exact same line. It would look like this line right here if we were to flip it upside down. So this one is odd as well. And then number 6. Number 6 is not symmetric to the y, not symmetric to the x. So this would be neither. All right, if you have any questions on these, please call me over. Otherwise, let's move on to our final task. All right, so for number 7, your goal is that you are given the part of a graph for function f, all right, for a partial graph of f. We want to complete the graph in the case that f is an odd function and in the case that f is an even function. So what I want you to do first is look at number 7 and come up with some approximate points. Okay, so for number 7, we've got a point at 0, 0. We've got a point right here, and let's say it's touching this point right here, okay? So let's approximate this to 2, 5, okay? And then we've got this point right here. Let's say this is 4, 0.5. And then we've got this point right here. Let's call this 3, 6. And let's just say it's touching, let's just round up, okay? So 6, 4. All right, so now what I want you guys to do is, if it's an even function, what we know about even functions is that it reflects across the y-axis if it's even, right? So what this means is if it reflects across the y-axis, that means all of our x values become negative. All right, so we're going to take our points that we just came up with and make all the x values negative. So for 0, 0, it would stay the same. It would be right there. For 2, 5, now this becomes negative 2, 5. For 4.5, be negative 4.5. And then 6, 4 would be negative 6, 4. And this is what our graph would approximately look like. All right, so that is if f was even and we reflected across the y-axis, there's our graph. Now, if f is odd, this means that it's going to reflect the x-axis, all right, or if you want to think of it as the origin. All right, and what that means is that our x values stay the same, but all of our y values become negative. So 0, 0 stays the same. Then we've got 2, 5, but then it would become 2, negative 5. 4.5, so 4, negative 0.5. and 6, 4. So that would be 3, 6, negative 4. And this is what our graph would look like if it was reflected across the x-axis. All right, so this is what happens if we were to say our partial graph of f. If it was even, it would look like this. And if it was odd, it would look like this. Now, I want you guys to try the second part, the part down below. All right, when you come back, I'll have the answer written on your screen and we'll go through it together. All right, so go ahead and try to do this one on your own, just like how we did the first one. And when you come back, I'll have the answer on your screen and we'll go through it together. So go ahead and pause your video now. All right, so your graph should look something like this. If you got them right, then you are done for today. Look to the board to see what to do next. Otherwise, keep listening and I'll explain how you should have gotten this. So first thing we wanted to do was identify points for our partial graph of f. So we've got 0, 0, 3, 6, 5, 2. Then, if f is even, that means it's reflecting across the y-axis, so all of our x values will become negative. All right, if it's reflecting across here, we're going across, all the x values become negative. So we take these points, we make 0, negative, 3, negative, 5, negative, and keep the y's the same. Plot them and connect our dots. If f is odd, that means reflect across the x-axis or the origin, and all the y values become negative. So we make all of the y values negative, plot our points, and there's our graph. All right, so I hope you learned a thing or two about relations and functions today. If you have any questions, please call me over so I can help you. Otherwise, look to the board to see what to do next, and I hope that you have a great day.